Hello, my name is Michael Pritchett, and for my project, I decided to make a genetic algorithm. I actually have some experience with genetic algorithms due to taking Dr. Taylor's CS 5401 evolutionary computing class. In that class, we made genetic algorithms to make the most optimal keyboard layout, but I'm getting ahead of myself. What is a genetic algorithm? You see, genetic algorithms are a computer science way of mimicking Darwinian evolution. For example, say we have a bunch of fish in a fish tank, and every so often some food pellets spawn in. Now, the fish are aware of where the pellets are and know how to get to them, but let's say for the sake that their only difference between them, their genes, are how fast they are. Now, naturally, you do need to eat to survive and then have kids, so that if the only gene is speed, we can naturally expect something to happen. Over time, the ones that are faster get to the food first and live longer. And in this essence, it's evolved, this trait, this gene. Its speed has been maxed out. Now, we didn't tell it to, we didn't force it to, but due to natural evolution, it did. The ones that were faster were more fit for their environment and therefore thrived for longer. And that gene was passed down because of that fitness. And that's what we try and emulate in our computer science genetic algorithm. A genetic algorithm can be broken down to certain components. The gene, the individual input or smallest bit, the chromosome, which is made up of multiple genes, the fitness of a particular chromosome, and the overall population of chromosomes. In Dr. Taylor's class, when we were designing the most optimal keyboard layout, what we did is we set up the distance between keys as our fitness. Ideally, you don't want to move your fingers. The most optimal keyboard means that you move the least amount from the home row. And so what we did is we took in a bunch of data. We'll say in this instance, an entire English dictionary. And we said, how quickly can we type every single word using this keyboard layout? And what it did is it tried to spell every single word by going from one key to the next, from where your home row would be on your fingers. And as it did this, it got a total distance that each finger needed to move, and that became that keyboard's fitness. The keyboard layouts with the highest fitness then went on to merge with the other high-ranking keyboard layouts, to then spawn the next generation, and this process repeats itself with changes happening between each generation. When we have two parents passing on their genes to the next generation, this is called the crossover process. After enough of that crossover happens to make a full new generation, the process repeats in its entirety. Once again, fitness is evaluated for each keyboard layout that has come from the previous generation. They are scored, and only the top echelon is chosen then to reproduce and have the next generation. This process continues until we reach a convergence. Essentially, you'll get a couple different results that are all fairly similar. And that is pretty much the peak or the end of the possible solution. Here we have one of the most optimal keyboard layouts for the given data. Now, the data given actually dictates what kind of keyboard layout we would get. For instance, if we switched over, instead of just using an English dictionary, to, say, some Java code, you'd see that certain keys are in different positions because they're used more or less. Now that we know what a genetic algorithm is, let me talk about how I used it for my project. I decided to make an AI play a video game. Now, at first I wanted to pick something a little bit more visually stimulating, something like Bloons Tower Defense or Plants vs. Zombies. But I do not want to actually make a game, I want to make an AI. So I looked online to find something open source. I came across an open source library of, in Python code, Super Mario for the NES. This was actually built off of OpenAI's gym environment, which is a perfect playground for AI, having certain built-in features like a list of moves for the AI to choose from, a built-in fitness function, which I did end up using for a little bit, but ended up not sticking with, and a list of important information that the AI would use as input. My goal was to make an AI that's comparable to the human limit. The world record speedrun for 1-1 on Super Mario Bros. Has 370 left on the timer by the time they reach the flag. So my goal was just to get close to that, at least, if not beat it. So, how did I do? Not so good, actually. Don't get me wrong, the AI tried its best. It's just really slow. First, let's start off with the structure. Each individual Mario agent was made up of a series of inputs. Those were its genes. The number of genes per Mario agent was defined by me to speed up the training process, limiting the number at first for early growth and then expanding it further to let it make more decisions. At first, the genetic algorithm was very basic. I wanted to keep things simple and just start by running the thing. So my fitness was just move right and don't die, preferably. And the crossover was just 50-50 whether or not you got the action of one parent or the other. Then I worked to improve this, to speed up training and reach a better convergence. For the crossover method, not too much actually changed from the beginning, at least not with the crossover itself. I more so focused on the selection method that I chose of the parents and changed that over time. Throughout the entirety of the project, the crossover method stayed as taking each action one at a time and 50-50 between either parent 1 or parent 2. This will be a problem later, but I'll get back to that. After the crossover process, I would chuck it into the mutate method, which would go through each action and roll the dice on whether or not it would mutate based off of the mutation rate that I set. If a gene was chosen to be mutated, instead of choosing between one of the two parents, it would actually pick a random action from the list available. My selection method became a bit more advanced over time. At first, I was just doing something simple like just the top 10% or just the top 100, but then I started a roulette selection. A roulette selection takes the fitness of each individual agent and uses that as a weighting, heavily favoring those with higher fitness. But lower fitness still have a chance of entering the gene pool to keep things fresh. But I ended up with a mix of a roulette system and a bit of elitism. Elitism allows for high fitness agents to continue onto next generations without the need of a crossover. This was done to speed up the learning process since it was still painfully slow at this point. The fitness function I iterated on several times throughout this project. At first, it was very basic, like I said. Reward for going to the right, punishment for going to the left and standing still, and major punishments for dying. Also, a slight punishment for living. I wanted it to focus on speed, so the faster it completed its goal, the less punishment it would take. And that worked, kind of. It developed a little bit of a quirk where, even though it was still much more beneficial to live, it tried to kill itself as quickly as possible. And it got really good at it, at least. It sprinted to the right into the first Goomba. And it was just stuck like that for a good long time. Until it eventually figured out jumping over the Goomba was a lot better than running into it. Granted, it then jumped over one pipe and then got stuck at the second, slightly taller pipe. The AI being a series of inputs was not the best idea, because to reach certain pipes and height, it needed to hold the A button for several frames in a row. Now, the odds of that happening were there. It just took a long time. So I changed the fitness function, hoping for quicker learning and a faster convergence on more optimal movement. The fitness function I used next was the built-in one, once again rewarded for going to the right, punished for dying, stuff like that. Very similar, actually. Added a couple other things that I didn't have, like bonus points for killing a Goomba, getting some coins, picking up a power-up, but it didn't help too much. It quickly fell prey to the same trap that the other fitness function did. It just couldn't jump over the really tall pipe. And when it did, there were more Goombas on the other side that would kill it before it figured out how to jump over the next really tall pipe. Finally, after doom scrolling a bit on my phone, I came across a YouTube short that actually was about the very same topic. Someone was making an AI to play Super Mario Bros. I took a look at their fitness function and once again had similar aspects of praised for going to the right, punished for staying alive too long, but it introduced something new, an early exploration bonus that I hadn't considered. Plus, the equation looked cool, so I nabbed that, changed it up to actually fit my algorithm, and got some decent results. Once again, it was a slow process, but it did improve over time. And that's pretty much it for the genetic aspect of the algorithm. The Marios are made up of genes. The genes are the inputs. The inputs are crossed over from parent to parent. The fitness is evaluated based off of how far they made it. But there's still some more code to go over. When it came to actually training the AI, I wanted to be as efficient as possible. So I tried my best to use some parallelism. That means trying to have multiple things run at the same time. Since for training purposes, I decided to use 100 generations of 1,000 different agents, I needed some way of processing all that as quickly as possible. With the parallelism that I used, I was able to use my CPU and all of its cores. Normally, you would want to use your GPU for this because it is faster and more efficient. However, due to the environment that I was in, this NES emulator using Python, I was limited to my CPU. A quick Google search told me that PyTorch was not compatible, so I gave up on that idea. So with my CPU running 12 cores at 4.3 gigahertz for several days, I was able to effectively train a couple batches. To further increase this efficiency with training, I opted out of any visual component of the emulator. Instead, I wrote a separate script that took inputs and played them out in a visual format. And with each individual agent just being a series of inputs, I could use that as an input for the replay script. I then modified it further to play multiple at the same time, so that I could create this visual spectacle. Not only is this a good representation of the multiple agents training at the same time, but it's also a showing of the best of each generation, sequentially getting slightly better each time. Kind of. And another way to be more efficient with my training was to create this checkpoint system. When collecting the best agent of each generation, I compared them with each other to keep a best overall agent. I used this as a checkpoint system, so that when the code started again, it wouldn't just start from ground zero, but instead take that best overall agent and use that as its new first generation. This allowed me to start and stop the process whenever I needed to use my computer for other important things. And with all the code reviewed, it's time to circle back to what I said before. I messed up. Big time. By making each agent just a series of inputs, I made crossing over a nightmare between them. You see, as each agent is just a series of inputs, when you try to compare input 1 to another input 1, and input 2 to input 2, certain things can kind of get out of sync. Let's say we have one agent hold down the A button for 5 frames to jump over a pipe, but another high-scoring agent only held down the A button for 3 frames because they were sprinting beforehand, and that momentum helped carry them up and over the pipe. Now when they cross over, let's say that their child jumps for 4 frames, but statistically, it would only have been sprinting for half of the frames, so its momentum would not be there, and it wouldn't clear the pipe. Instead, it's now stuck behind the pipe, thinking that it's in front of it, carrying out all the other actions of its other 2 parents, thinking it's reached past the pipe. But in reality, it's bashing its head against a wall. And so those 2 high-scoring parents made a horrible offspring. This is what was slowing down the learning process immensely. I was handicapping myself with this. And at this point, it would be more efficient to just mutate than cross over. Since if we wanted that individual to reach over the pipe, we just have to hope that one more frame was turned into a jump. And this kind of off-syncing of the inputs happened many times in many different scenarios. Now, that's not to say that this algorithm didn't work. It functioned, and it would reach the peak, most optimal series of inputs to beat 1-1. However, it would have taken a very, very long time. It would just need to get very lucky on some mutated genes. So with me telling you all that, you're probably wondering, what footage am I showing right now? Well, I can assure you that this is my genetic algorithm. I cheated. For the sake of time, I decided to make another Python script. This one allowed me to play the game manually and record my inputs. And since the Mario agents are just a series of inputs, I was able to replace the best overall agent with my inputs. The algorithm did do a good job at iterating over this though. It shaved off another 5 seconds from the timer from what I left it at. It just took 4 days to do so. So where do I go from here? How do I make it better? Well, first of all, I don't use a genetic algorithm on its own. That should only be done for very simple tasks that can be efficiently calculated, like the keyboard. Playing Mario is a bit more complex and a bit more taxing on my CPU. Instead, like in the YouTube short that I found, a neural network plus a genetic algorithm is actually the most optimal solution here. With the neural network, I would also give it more of an input so that its choices, its decisions about what actions to take are actually based off of something and not just completely random. I'd let it actually see the level and what's happening around it, and it can make decisions based off of that. Once again, it would just be a series of inputs, but this time with some reason behind them. And the genetic algorithm would kick back in. It would take those series of inputs, weigh their fitness, roulette style pick some parents, cross them over, and spit out some new ones. But the neural network allows it to learn more and quicker. Not only would this train one of the most efficient series of inputs for 1-1, but it would actually create a AI agent that is good at Super Mario Bros. It would still take some time to learn each level, but not as much from the first time. It would still retain some of the decision making, like an enemy in front of it or certain block placement, and make those same decisions based off of those inputs. It would learn. So while I fell short of my goal of making the genetic algorithm comparable to the human limit, I still learned a lot, and I hope you did too. Thanks.